Hey, welcome back to Fat Mama Physics. In this video, we are going to apply Faraday's law of electromagnetic induction. So, here we go. We have example 1. I will also do example 2. And in the next video, I will do example 3. So, I assume that you, first of all, understand how Faraday's law works. I also expect that you understand how Lenz's law works and also know how to apply the right-hand rule to determine the direction of the current flow using Lenz's law, okay? So hopefully you may have had a chance to try these questions. So if you struggled a bit, let's see how we did. Starting off with a square loop of wire, and this guy is perpendicular to a 1.5 Tesla magnetic field, which we don't know which direction. Let's just pick a direction for now. If each side of the wire is 1.20 centimeters, what is the magnetic flux through the loop? Okay, that's not too bad. Magnetic flux, and assuming this is perpendicular, so we know that the angle between the field lines and the area is 90 degrees. So we know that cosine of 90 degrees is just equal to 1, so we don't have to worry about that cosine term when determining the magnetic flux. So let's start off with the magnetic flux, which it looks like this little phi looking sign here. We can go ahead, NBA, so that's the talking about the basketball league, and the N looks like this guy is of a single wire, so I don't think there are many loops, so N is just equal to 1. The field is given here, and the area is that of a square, so we just have to take 2.1, which is going to be 0.021 meters squared. So, we can, let's put it in the end. Okay. So after we combine all of these together, we get 1 times 1.50 Tesla times 0.021 meters, all of this squared for the area. And this is going to give us, here, give her that equal sign. I get 6.615 times 10 to the power negative 4 Weber. So that's just 6 rounded to what, 2 sig figs? Or 3 sig figs? This is 3 sig figs. So 6.62 times 10 to the power of negative 4 Weber. Right there. Okay, so that was the first question. Done. Okay. Not too bad, eh? Example 2. A 1.8 diameter, and doesn't say what diameter coils, so I'm going to assume this is in centimeters, because if that was in meters, that would be a hunk of big, huge coil. So, it's a lot of wire. But we'll see. We'll evaluate at the end. Anyways, we have a circular coil this time. So, we got a circular coil. And this guy is 1.8 centimeters in diameter. Okay, so we have to get the radius, I guess. It's 50 turns, so that's at the N value. Our N value is equal to 50. Okay, it's perpendicular to, again, doesn't tell us the direction of the magnetic field, so it's perpendicular, so we'll just do into the page, because I like crosses. They're more distinct than circles. This is going to give us the magnetic field, so that's going to be our B value. If the magnetic field is reduced to 0 in a time of 0.1 seconds, that's just going to be our time. What is the average induced EMF in the coil? So to find the EMF, this has to do with the number of coils times the change in flux over the change in time. So it's essentially this whole thing that is changing, how the magnetic flux linkage is changing over time. So I'm just going to put that negative sign there. It's just for direction of current. It actually serves no purpose in terms of giving us a value. So But we do know that the magnetic field is reduced to 0. So we kind of have to look at the final minus the initial here. So final, we know that's just going to be 0. So the n value is still going to be 50, but we know the b here, actually here, let's just do the change. The change is we go from a 0 Tesla minus 0.250 Tesla, which is what we had to begin with. And all of that was done in a span of 0.100 seconds. And we're going to get a negative number, but that's not going to matter, okay? Oh, and don't forget, the flux linkage is not just the magnetic field, it's multiplied by the area. So just to get a sense of our area, this is a circular loop, which is the radius square times pi. I just did that in the opposite order. So we need the radius, which is 1.8 centimeters divided by 2, since that's our diameter. And we need to convert that into meters, so that's just going to be 0.1018 the meters divided by 2, all of that squared times pi, which I have over there already. Get a little cramp here. Oopsie. So I'm just going to add this area here. The area is not changing. The field is. So that's just going to be pi times 0.018 meters divided by 2, and that squared. Okay? So the top is going to be n. Oh, I forgot. N is just going to be 50 number of coils. So that's going to be 50 times 0.25 effectively, times pi, times in brackets 0.018 divided by 2 squared, and divided by 0.1 seconds. So this gives me 0.0318. So in fact, I think the original intention of this question was 1.8 meters of diameter circular coil. Well, actually, so it seems like the original intention of that question was in meters. That's a huge circular coil. So I'm gonna keep it as centimeters. But yes, if you had that as meters, you would get 320 volts. But I think this makes a little bit more sense, which what I got was 0.0318 volts, or this is rounded up to 32 millivolts. Okay, there we go. Okay, I'm going to change that. Otherwise, imagine that huge hunk of coal. No one's going to be able to afford that. No, I'm just kidding. They will. It's just where to divert your priorities. Okay, so that's the first question. So this one, we... So this one was easy. The magnetic field was just changed to 0. Okay, so directly you could just use 0.25. But in the next few questions, the magnetic field not only may change magnitude, but the magnetic field may change direction as well. So that's something else that we should probably practice. So here we go. We'll just stop the video here, and the next video I will do example 3, and I probably will do a tag-along question of that as well. I thank you for watching. Hopefully this video was helpful, and good luck, Fat Mama Physics, signing out.